Okay, finally, short section. So we're going to do this a little bit differently. So I'm going to explain sort of the basis of the functions and the defined calculations that they can do. And then David and Tara will do some sort of hands-on demonstrations to the screen of using the MATLAB and the Python functions. So this is exactly the same model as the standalone programs. Indeed, it's mostly the same code. We're just accessing it a little bit differently. And these functions, they do one calculation at a time. So if you have multiple problems, you need to construct your own loop in MATLAB or Python to run through the data. So what have we got? The two functions, they're both called MarChemSpec, and they can be run, they're different of course, they can be run from within Python and from within MATLAB. There are 7 different types of calculation using artificial seawater, which we're not going to discuss, and seawater and the trace metal models. Really just the simplicity of input, there is no difference calculation corresponding to MCS delta for these functions. How do they work? They receive input data only via their arguments or parameters, depending on what language you use, and they return results in the same way. So they don't write to files. They do read a few files, but they do not write to them, and you do not need to write any input data files either. The functions, they call a Fortran library containing the model. The code reads a few of these standalone, these input files that or files, I should say, that you don't need to worry about. They just have to be present. They solve a single problem at a time, and you don't need to know anything about Fortran to use any of these functions. So what do we provide in the download? We presented a set of 7 example scripts for both Python and MATLAB, illustrating calls using the different calculation types. So in Python, you'll see a file called MarChemSpec.py, which contains the wrapper function. And this, because I'm told it's the Pythonic thing to do, it should be placed in the same directory as the example scripts, and we assume that you do that. In MATLAB, there is a file, MarChemSpec.either .mexw64 or MEXA64 if you're a Linux or Apple user, and that contains the wrapper function for MATLAB. And then also, there's a Fortran library file, which will have an extension .dll for Windows, or .so, excuse me, .so for shared object Linux, and there are some associated directories and text files. I'm going to cough a moment. And let's see, we don't have an Apple version of these 2 wrappers yet. We just managed to scrape out doing the standalone files last week, and we haven't got any further with that. So it's Windows and Linux only at the moment. There are 2 supplement documents that describe in detail each of the 7 types of calculations for which there's an example script. And there are also, I think, as just plain text files, there are 2 technical notes that summarize the characteristics of the Python and the MATLAB, not MATLAB, code for the two wrapper functions. But I don't expect people, unless they're programmers, are going to be interested in that. So what are the files that we provide in the download? There are these grayed out files which will get read, but you don't need to write anything to them. You don't need to look at them. There's the MarChemSpec library file, either DLL or shared object, the MATLAB wrapper function, and in the case of Python, the MarChemSpec.py file, and there's a subdirectory examples which contains all of the scripts. These two other subdirectories which contain information for calculating uncertainties. And this file, which says very boldly, do not delete .txt, which is just a marker. It means that the program looks for this as the parent, is representing the parent directory of these two other directories. If it didn't find that, it would tell you that something was wrong. So again, something you don't need to worry about because it's grayed out. We did discover when we set all of this up that there are a few things that you need to get right, and it's basically about the wrapper knowing where to find the library file, which contains the Fortran executable, and the executable knowing where to find the files are that it needs to read. So in the MATLAB case, if it's interactive MATLAB, I think there's a set path command or an add path command that you can use sort of in your MATLAB session. And in Linux, it's a little bit more complicated, and you really need to read the supplement. There are two commands, variables that need to be set, environment variables, perhaps LD preload and LD library path, and they're described in the manual. And also, the Python function has an argument called DLL, which you set to the path and the name of the library file. And in each of the scripts that we provided, there are lines for you to make those assignments. So if you read those scripts, don't just try to run them as they are in the distribution. You read those scripts and make those assignments, you should be okay. And the reason why you have to do it is because it all depends on where on your computer you put these files. And once you've got these things right, the input data in your function call are all you have to think about. That's all. I'll just note, lastly, the names of the library files turn out to be slightly different, and this apparently is a necessity, and you can find this in the documentation. Windows, there aren't really any restrictions, except you need the extension .dll, so we just call it MarChemSpec. In the Linux case, it turns out that either the operating system itself or MATLAB wants to see lib as the beginning of the name, so we had to call it libmarchemspec .so in order to get the thing to run. So what can go wrong? It helps just a little bit to understand how this works. So you call this wrapper function. It tests to make sure you've got valid arguments. Are they the right type? Are they numbers rather than characters? Are they the right size and shape? If they're not, you'll get an error message. If everything's okay, they're passed to the underlying model. And that's where all the data, the content of those arguments, is tested to death. I mean, we really tried to test everything. And if there's an error there, you'll get an error. The wrapper will come back to you. You'll get an error message, and you'll see what was wrong. Now, if somebody manages to get something that's not right beyond our tests, and it goes deeper into the Fortran model, and an error is detected later on, then it's not going to come back to you. It will write an error message to a file, and then it will stop. And depending how you're using the MATLAB or the Python, I'm not quite clear about this, but if such a stop happens, you might well get kicked out of your MATLAB or Python session. You think, whoa, what happened? And this is what happened. A mistake got far enough into the code that the program had to stop. And if that happens, have a look and see if there's a file which might have an extension .err for error, and see what that says. And if you can't figure out what's going on, that's a time to tell us what you did, and then contact us with that information. But this business of having to doing a hard stop, it's not really avoidable unless you have the entire program can always make its way back up the chain of subroutines and come out at the top with an error message. And when you have thousands of lines of code and hundreds of subroutines, that becomes quite awkward to arrange. So I said there are 7 different types of calculations. What are they? So the first 3 involving artificial seawater I've grayed out here, and I'm not going to bother with. iCalc, which is the integer argument that we tell the wrapper, what sort of calculation is it going to be. iCalc equals 4. Seawater of specified salinity with an adjustable alkalinity relative to that of the seawater of reference composition. So in that case, nice simple input, nice, easy to understand. That's a good example to try, which is why I put a star next to it. iCalc equals 5. Natural waters of arbitrary composition, same seawater ions, but that means you have to input all of the concentrations, either as amount contents or as modalities, just as you did for the standalone model. You do that as an array in your wrapper function. Then iCalc equals 6. This includes trace metals, but otherwise the input composition is just salinity and temperature. And the trace metals are added, and the output is the fractional speciation. And, excuse me, most complicated of all, iCalc equals 7. You've got the trace metals again, but you've got the natural waters of arbitrary composition. So there's quite a lot of values to input, although we've cut it down from that 100 to kind of the minimum number to make it to simplify the input. So you might find that easier than the standalone programs. We've tried to cover most of the sort of natural uses of the model, and the outputs are the seawater state parameters and the uncertainties and so on in just the same way as the standalone case. So in the last 2, I think it's the last 2 slides, or last three or so, I'm just going to summarize the kinds of things that you'd see when you open one of these scripts, and that is a MATLAB case. So you see here there are 2 variables with nothing assigned, and this is where we're telling the Fortran model where to find its files, the grayed out ones that I showed you, and then the uncertainty-related files, and actually they're just the same, so you just need a directory to put in there. Then you'll see in the script there are some fixed values that are assigned that you don't need to change. Then the next step, you put in your input variables. So this is temperature. In this case, we're in centigrade, so it's 25 degrees, salinity 35. And MH, I mean, because it has sort of multiple duties, it's not very well named, but this is how you adjust the alkalinity up and down from the value for reference seawater. And in this case, we're not doing anything, so we leave it at 0. And finally, you call the function, and that's a MATLAB call of MarChemSpec. So these are all the input values here, which you will have assigned, and in the square brackets are all the outputs. And all of that is explained in the manual, and we do it for every single iCalc case, for all 7 cases. So the analogous Python script, kind of similar. There's a library path name to enter. It's where to find the DLL or shared object library. And a specifically Python thing, importing the MarChemSpec function from the MarChemSpec.py file, which turns out to be from MarChemSpec, import MarChemSpec. Then assign the 2 directories which I mentioned for the MATLAB case, which is where the Fortran file, Fortran program element of this, the library, will find its files. Some fixed values are assigned again, then your user input. And in this case, I've up to the alkalinity, changed the alkalinity 5.01, and then there's your call of the Python wrapper underneath. And after that comes back, then you can examine the results. So all of the 7 examples are structured in exactly the same way. Keep things as simple as we can do. So now, that was the only thing that I wanted to show, or the last thing that I wanted to show. So David will do the MATLAB example. Then I guess we'll swap computers, and Tara can do the Python example. And at that point, if anyone has got any energy left for any questions or other calculations, then we can do that. And then I would guess finish probably by about 5 or so.
Yeah. Okay, thank you, Simon. I'll quickly do a couple of things with MATLAB. The first is so you can see what the output actually looks like. I will set this example number 4 going. I need to get this out of the way so I can do this. I'll set this going, and I can show you some things about the script there as we go down. This, that Simon mentioned, we have to put in the top main directory of the MATLAB installation here for these 2 files, which I've done here on this computer. There are then a series of fixed values that we don't change for this, and then the user-defined values, temperature, salinity, and possibly an alkalinity change. And then the results appear then in the workspace. There are, again, C species or amount contents, and they're set up in very much the same way with cations, anions, and neutrals. And there are others of you can also find in the manual that the species the state variables are there as well, and the names of these species you can look in the manual, or they're also in the output, so you can put them there. So all the information is available to you then. So that's one thing I wanted to show. Simon said you can put things in loops. So this is a little script I've done here with this iCalc 5, which I've modified a bit. One thing to see here when you put these in, you need to put the species in the right places, but I've set out here in these files which species you put in and where they go in the arrays. So when you can just edit this for whatever composition you're interested in. I've also put in a charge balance check so that should it be unbalanced, you'll get a little message telling you it's unbalanced and how much. It doesn't have an automatic correction. You then have to go back and fix your own correction. What I did then was to just look at the effect of adding a bit more carbon, in other words, CO2 uptake to the system. So you can put this call to MarChemSpec in a loop very easily. So here I've taken the initial DIC and then added steps of 10 micromolar, and then pulled out of there the pH and the uncertainty in the pH, and do a simple plot of that. Since this involves running it 10 times, it takes a little while. I'm back on the DIY approach. Here's one I did earlier. When it decides to load itself up. And so you can get a nice plot. Here's the pH change then as you increase the carbon. One thing to notice, if you remember when we looked at used the delta, looked at the change in pH, the uncertainty was actually fairly small. But with the individual pH values, the uncertainty is quite a bit larger. So you see that very clearly comparing those two examples. The only other thing I thought I'd show is in the, I'm not going to try and run it, but the example script for number 7, which is including trace metals and a free composition where the arrays are much larger. Again, I've put in here where the particular trace elements go. In this case, the trace metals, I've just put them all as 10 to the minus 8 as an example, but of course you could use these elements in the arrays and put in your own numbers. So that's the way the MATLAB works. It's very flexible. You get all the data out that you can then do what you like with, and it's easy to do things like I showed of putting in a loop so you can look at changes that are happening. The main fiddly part is making sure, again, the inputs go into the arrays in the right place. But you should be able to do that just by taking the example scripts and editing them with the numbers you want.
Yeah, they are all detailed in the manual too, and one of the output arrays contains the names of all of the output species. As I think David said, I think all of the things that we calculate in the standalone model are also output by the wrappers in various arrays.
Okay, so that's me done. So now hopefully things will work. We'll switch to Tara's computer here.
Okay, so I'll just give a quick demo of the Python wrapper and the examples we've written here. I'm doing this on a Linux server, so it'll look a little bit different if you're on Windows. And I'll try to note where that would be different. So I'm just in my terminal on Linux, and I'm in the base MarChemSpec directory. So that's, for me on Linux, that's just home, user, and then the MarChemSpec Python directory. If I list the files in here, you can see I've got the MarChemSpec library. Oh, okay. I've got the MarChemSpec library shared object file, and then there are a couple subdirectories, one of which is the examples directory, which contains all of the example Python scripts. And these are essentially analogous to the MATLAB example scripts, just written, of course, in Python. And so in my TextEdit app, I can open any of these examples. So this one, I'll make this bigger, is, again, iCalc4. So this is just the base, the most basic case. As David was showing, we have a bunch of fixed variables that you shouldn't change. And then, as Simon said, there are 3 things when you open this file that you will need to write in yourself. The first is the path to the shared object library. And that, like I just showed you, on my Linux server is just home/user/MarChemSpec Python, and then you have to include the name of that file, which is libmarchemspec.so. So again, just over here, that was in this directory. The second change to make is to assign the location of the parent directory. And so this is telling the program where all the files are and where the Fortran needs to look for things. So for me on Linux, that is still home/user/MarChemSpec Python. And I've included the trailing slash there at the end, but there is no file name anymore. It's just the location of the directory. And so if you're on Windows, all of these file paths will look a bit different. The slashes will go the opposite direction. But I think in terminal, you can still just determine where you are by typing pwd. So once you've done that, and so again, I've done that for the iCalc4.py example, that should be ready to go. And so to run these scripts from Python, the easiest thing to do is to just do them directly from the command line. You can, of course, later write your own wrapper, loop over things, as David was showing, but for right now, I'll just show you the direct command line example. So the way to do that is just type Python, and then you're going to type the path to the file that you want to run. So you'll notice that I'm still in the MarChemSpec Python directory. And so if I want to run a Python script that's in the examples subdirectory, I need to type examples/iCalc4.py, and I'll hit run. So to make this a bit bigger, this is the same output that you would get for the MATLAB case, except that it's printing directly to your terminal, your command line, instead of in the MATLAB GUI on the side of the screen. So I've got all the seawater state parameters in this column, and then their uncertainties in the column next to it. And then at the bottom, all of the species concentrations and their activity coefficients. The iFail value at the bottom is 0, which means this ran successfully, and it will always print which version of the calculation you're running. Like Simon said, there are a couple types of errors that you can cause when you're running this. One is basically a Python error, so something like a syntax error. If I create an error like that and I try to run this file again, I will get an error that's telling me something's going wrong with the running of the code itself. It's not a model error, it's just that something in the file is incorrect. So that's the first case. And if I fix that, the second type of error is an error in the model itself, which you can cause by introducing an input that's outside the range of validity. So if I change the temperature to 125 degrees, and try to run this. Actually, I'll clear so you can see this easier. And try to run the model again. I get an error that's telling me that the input temperature is much too high. And so this kind of error is hopefully more helpful. It'll tell you exactly what you're doing wrong. But if I go back and change that, everything should run fine. And so running Python directly from the command line like this, you should be able to run all 7 of these example scripts. And then if you wanted to write your own wrapper or use a notebook or something else, you could basically copy and paste all of that information and run the function exactly the same way. But for now, yeah, I would just try the example scripts, and all you have to do is fill in those 3 strings at the beginning to get going. I think that's it.
Thanks very much, Tara. That was really clear. I guess actually this kind of brings us to the close after a long 3 hours and a bit. So before we finish, this is a time for any general questions anybody wants to raise and speak out loud, or if there are any particular problems with stuff they're running on their computers or have been trying. Now is a good time to do it in person, Otherwise, we'll have to look at the questions remotely by email in the usual way. So if there's anything anybody's got the energy to ask now, please do. I don't think I have any takers. Okay. Right. Well, in that case, I should say thank you very much for coming. For the first MarChemSpec tutorial, I hope there will be others. Well, there will be one tomorrow, but I hope there'll be others over the years. And if you're having trouble applying the models to your work, or you have any questions, just email me if it's the standalone models, probably MATLAB, contact David. If it's Python, definitely Terra, and we'll try to help you. So, thank you so much.